when replacing a 3000 amp lateral to an overhead and installing a 3000 amp breaker outside, making it a new service entrance, the existing 3000 amp becomes a feeder. The equipment grounding conductor, or EG, sizing for parallel feeders and raceways can be addressed using specific exceptions within the National Electrical Code, specifically 250.122F exception No. 3. This exception allows for a reduced EGC size under certain conditions. The scenario involves 8 parallel 500 kc mil conductors in 3-inch conduit. According to 250.122F exception No. 3, the equipment grounding conductor can be sized as small as the phase conductor for parallel feeders that are in raceways. This is a departure from the general rule in 250.122, which often requires larger EGC. To calculate the minimum size of the EGC, the formula is EGC size equals the number of parallel conductors multiplied by the phase conductor size. In this case, EGC size equals 8 times 500 kc mil, which equals 4000 kc mil. However, since 4000 kc mil EGC is not a standard size, the next larger standard size must be used, which is 500 kc mil. While using a 500 kc mil conductor would satisfy the exception, it's crucial to understand all the requirements before deciding on the final grounding method. It is indicated that the conduit is to be used as the equipment ground. The NEC permits using metal conduit as an equipment grounding conductor if it meets specific requirements outlined in 250.118 and 250.118. These requirements ensure the conduit's integrity as a reliable grounding path. Firstly, the conduit must be electrically continuous, meaning that all sections and fittings are properly connected to create a continuous, low-impedance path to ground. Secondly, the conduit must be bonded to the service equipment grounding conductor at the service entrance. This connection ensures that fault current can effectively flow back to the source. Thirdly, the conduit must be bonded to each enclosure that contains the feeders. This bonding minimizes voltage differences between enclosures and the conduit, reducing the risk of electric shock. Meeting these requirements is critical for the conduit to serve as a reliable EGC. It's important to note that even though the conduit can be used as the EGC, it must still meet the code requirements for grounding path impedance. This means the conduit system must provide a low impedance path for fault current to return to the source, which helps to ensure that overcurrent protective devices operate quickly and safely. The exception in 250.122F No. 3 allows the downsizing of the equipment grounding conductor. This is provided the parallel feeders are installed in a raceway. However, this exception does not negate the requirements in 250.4F, which discusses the effective ground fault current path. The effective ground fault current path must be permanent and electrically continuous. It must also be able to safely conduct the maximum ground fault current likely to be imposed on it from any point on the wiring system where a ground fault may occur to the electrical supply source. The ground fault path must also have sufficiently low impedance to facilitate the operation of the overcurrent protective devices in the circuit. The 3-inch conduit must be properly installed and connected to provide this low impedance path. This includes using appropriate fittings and connectors and ensuring that all connections are tight and free of corrosion. There are other important considerations related to using metal raceways as equipment grounding conductors. The integrity of the raceway system is critical. All connections must be tight and corrosion-free to ensure a low impedance path for fault current. Any loose connections or corrosion can significantly increase impedance, reducing the effectiveness of the grounding system. The use of appropriate fittings is also crucial. Listed fittings designed for grounding purposes should be used to ensure reliable connections between conduit sections and enclosures. These fittings are designed to maintain electrical continuity and provide a low impedance path for fault current. Another factor is the mechanical protection of the grounding conductor. While the conduit itself provides mechanical protection, the grounding connections must also be protected from physical damage. This may involve using protective covers or enclosures to prevent damage to the connections. It's important to verify the ampacity of the equipment grounding conductor. Although exception no. 3 allows the EGC to be sized as small as the phase conductors, it's still necessary to ensure that the EGC has sufficient ampacity to carry the maximum ground fault current. The ampacity of the EGC must be adequate to prevent overheating or damage to the conductor during a ground fault condition. Another code section that is applicable is 300.3b. All circuit conductors, including the equipment grounding conductor, must be installed in the same raceway or cable. This requirement ensures that the impedance of the ground fault current path is minimized, which helps to facilitate the operation of overcurrent protective devices. If the equipment grounding conductor is installed separately from the circuit conductors, the impedance of the ground fault current path can be significantly higher, which can delay the operation of overcurrent protective devices and increase the risk of electrical shock. Because this installation is considered a service, it is necessary to abide by 250.24c, which covers the main bonding jumper. For a service supplied by a grounded AC electrical system, a main bonding jumper must be installed to connect the equipment grounding conductors and the service disconnect enclosure to the grounded conductor at each service. This connection provides a low impedance path for fault current to return to the source. The main bonding jumper must be sized in accordance with 250.28. In summary, when installing parallel feeders and sizing the equipment grounding conductor, several key points should be considered. Firstly, review 250.122f exception no. 3 to understand when a smaller EGC is permitted. Secondly, calculate the minimum EGC size based on the number of parallel conductors and the phase conductor size. Thirdly, ensure that the conduit meets the requirements of 250.118 and 250.118 to know if it is to be used as the EGC. Fourthly, verify that all conduit connections are tight and corrosion-free. Fifthly, use listed fittings designed for grounding purposes. Sixthly, provide mechanical protection for grounding connections. Seventhly, verify the ampacity of the equipment grounding conductor. Eighthly, ensure that all circuit conductors, including the EGC, are installed in the same raceway. Ninthly, install a main bonding jumper in accordance with 250.24c and 250.28. It is also important to consult with a qualified electrical engineer or inspector to ensure that the installation meets all applicable requirements of the NEC and local codes. This can help to ensure the safety and reliability of the electrical system. In addition to the NEC requirements, it's also important to consider any local codes or regulations that may apply. Local codes may have additional requirements or restrictions that must be followed. For example, some jurisdictions may require a larger EGC than what is specified in the NEC. It's also important to consider the specific characteristics of the electrical system when sizing the EGC. Factors such as the available fault current, the impedance of the source, and the length of the feeder can all affect the required EGC size. A qualified electrical engineer can help to evaluate these factors and determine the appropriate EGC size for this specific application. Remember that the primary goal of the equipment grounding system is to provide a low impedance path for fault current to return to the source. This helps to ensure that overcurrent protective devices operate quickly and safely, minimizing the risk of electrical shock and fire. Therefore, it's important to take all necessary steps to ensure that the equipment grounding system is properly designed, installed, and maintained. In summary, correctly sizing the equipment grounding conductor for parallel feeders is essential for electrical safety. Understanding and applying the relevant NEC sections, including 250.122f exception no. 3, and adhering to the requirements for using metal conduit as an EGC will help ensure a safe and code-compliant installation. Always consult with a qualified professional and local codes to verify compliance. The information provided here is for educational purposes and does not constitute professional engineering advice.